No problem, sir. Just all the participants are joining. Just we have given the reminder. Okay, no problem.
Okay.
Good morning, participant. Good morning to all respected faculty members and participants. Welcome to today's faculty development program on AI, application of artificial intelligence in chemical engineering. It is a privilege to introduce our speaker for this session, Mr. Nitin Thakur, who is Chief Executive Officer of AB Engineers, an engineering consulting firm specializing in energy efficiency, process optimization, and sustainable solutions for industrial plants. Mr. Thakur is a chemical engineer with practical experience in chemical plant operations, refrigeration system, power plant performance, and CO2 emission assessment. His core expertise lies in applying AI, machine learning, and data analytics to traditional chemical engineering challenges such as heat exchanger and condenser scaling prediction, energy loss analysis, and process monitoring using real plant data from PLCS, installations, and IoT systems. Today, he will be presenting on heat exchanger scaling prediction with AI, demonstrating how artificial intelligence can strengthen core fundamentals and support smarter, more sustainable industrial systems. We warmly welcome Mr. Nitin Thakur and look forward to an insightful session. Welcome, sir. You can start your session.
Thank you. Thank you very much, ma'am. Good morning to all. My theme for today will be keeping more into context, like how. Anyway, let me go back. Let me do a restart. So I attended some of the session over the period. Like I think first day I attended. What I was seeing was that there is a more of an overview of how AI is applied to chemical engineering. And my topic was mainly on discussing the benefit of using AI for condenser scaling. But I felt like since yesterday I was thinking like, what could be more value addition or more takeaway for you guys to get a feel of it rather than just understanding like how we can use AI and what are the application. Like if there is someone who really wants to get his hands dirty and get a feel of it, like how it will be done in that context. So I will be first taking you into the what are the benefits of the AI into condenser scaling. Just a brief. This is something that Thadumal Shani Engineering College, Chemical Engineering Department, uh, students from third year helped me out in doing this. So this is something that some of you have already done it, got their hands dirty and worked on it. So this is more of that particular case I have chosen to give you an idea like what is this AI, how it is can be done by third year or fourth year students and go into this direction. If that is something that rings the bell in your eyes, that's something you have to do. So that is so yeah, it's doable. It's doable. Uh, One thing I would love during this session is If you have any questions or I want to keep this session more interactive. I don't want to be, I don't prefer to be a person who is speaking for like 2 hours and, answering all the question at the later stage. So jump in if you have any questions. It will be good. It will even keep me, it will just tell me that you guys are awake and not going to sleep. So just speak up if you have any questions and stop me anyway. I want to keep it more interactive than have a more of a running through lot many slides and then just just speak up. I mean, I'm open to take the questions as we go, and I prefer to have it so I at least know that you're getting the context right. So that being the setting that table, I want to go into what is uh, so first come first, what is the benefit of doing this condenser scaling? I just want to start with a story that I'm a great fan of reducing CO2 emissions. And if we have no choice of reducing the CO2 emission, then how we can recycle it? That has been my passion, and that's the arena I come from. So there was one case by the government of India asking for uh, consulting how AB engineers can contribute in reducing or recycling the CO2 emission that is being produced. How, how to do that? So, and this is Government of India mainly focusing on NTPC. So our first target was how to reduce it. So when we went into the direction of how to reduce the CO2 emissions, so let me tell you a bit about, how we went into that. So just give me a minute. So there now you guys already know that Delhi is suffering through all the smog, CO2 emissions. I mean, there is a visibility issue. There is PM10, PM2.5. They are going through that as a challenge. And even like, especially in this time of the year, like there is a big disaster going on for I think the better word is AQI. So the Delhi government is more and more thinking in that direction, how to reduce or how to make the AQI better. And one of the contributor is CO2. So when they came to us, AB engineers, we went and did a study like, what is really making this air quality really bad or AQI really bad. Uh, One of the thing that we told them was that really, like, their idea was mainly to clean the air that is already there in the Delhi area and make the AQI better. Our approach was a bit different. We said that rather than focusing on the air quality, why don't we focus on the industry that are mainly emitting that at a first place? So rather than going in the direction of really capturing the harm or the damage that is done to the environment in Delhi, why don't we first capture the industry? So one of the area that they felt that can be easily done is the power sector, because a lot of the power plants are owned by the the government body called NTPC, and they felt that that would be some place that they can do it easily. So we went in the direction of NTPC power plant. So now you know that there is a power plant mostly in India is coal fired. And if you know, the other option of the fuel is natural gas. Natural gas is considered more like expensive fuel than coal. Just to give you a context, I mean, very high level, like the cost of coal will be like, let's say 1.5 rupees per kg. I mean, I'm just making these numbers. They won't be real. The cost of natural gas will be like 15 rupees per kg. Okay. So in order to make the economics better for the production of power, coal is preferred. But when we look at emissions point of view, if I'm running coal, my CO2 emissions will be, let's just say, 1 ton. I'm just making a number, 1 ton per kilowatt. If I'm burning natural gas, it will be like 0.3 tons per kilowatt. So CO2 emissions is less when we are doing when we are burning natural gas, but since it is being expensive, we go for coal. So we didn't had the choice to tell that, oh, don't go for coal, jump for natural gas. Change. Imagine a scenario telling NTPC that, you change all your turbines and go from, instead of burning coal, you go for natural gas. I mean, that is a big, big no. So we understood that that is not the choice that we got. That is that is something not doable. So what else we can do to really reduce the CO2 emissions? So then we went in the direction of the conversion. So let's say when we are burning coal and to make 1 megawatt of electricity, we need, again, making a number, 1 ton of coal to make 1 ton of 1 megawatt of electricity. So how do we actually, I will take it back. I think I'll take it back. For making 1 ton of, for making 1 megawatt of electricity, I need 2 tons of coal. So where does this coal really goes? Like, if I really look at the distribution of the coal to make 1 megawatt of electricity, 1 ton of the coal basically goes into waste heat. And the remaining 1 ton is really the useful heat that goes into making 1 megawatt of electricity. So there is almost 1 ton of coal burnt that is called a waste. And we can always have a, we can always have a, we call this 1 ton waste as the efficiency. We can increase or in a way decrease the efficiency so that this 1 ton of coal that is a waste heat, we can optimize it. And that's the area that we took. So imagine just taking a number, 1 ton of coal that is a waste heat will be making 1 ton of CO2 emissions. So, and this is the area where we feel that we can optimize it. Just 1 minute, just 1 minute. Sorry for that. So now going into how we can reduce this 1 ton of waste heat or 1 ton of coal to make 1 ton of emission, CO2 emission, how we can do that by, utilizing the AI is what our subject became. And our target was mainly how we can, make this more efficient. So our entire game is in this arena, how we can reduce the coal consumption so as to reduce the CO2 emission. So that is the base I want to set, that is where this whole topic will go. So just I want to run through the slides. That is, what is the benefit? So we took, okay, before I go there, I want to add one more thing here. In a power plant, so if you look at the power plant, especially the coal-fired, very high level, there will be a steam turbine, okay? And the steam turbine, so there is this steam going into the steam turbine. There is a alternator to produce electricity. And whatever is the remaining steam, or what we were referring to as the waste heat, goes through this condenser. There will be water, and so there will be a cooling water coming in, cooling water going out, and this will be going out in the cooling tower. And based on that, this all will, cooling water will go out. So what we noticed was that the 1 ton of coal, which is a waste heat we are referring to, that basically is because of the scaling of the tubes inside the condenser, inside the steam condenser over here. So as the condenser scales, there will be a back pressure of steam on the steam turbine. This back pressure will then call for more steam to make 1 megawatt of electricity. Now, when it needs more steam, it means that it is calling for more coal consumption for making that 1 megawatt of electricity. So just to give you a number, like let's say if this was an ideal world and there was no waste heat, okay, so then we just need 1 ton of coal and we make 1 megawatt of electricity, and whatever is the steam condensing over here, that's about it. I mean, let's just say that is being 100% efficient. Now, let's say we take another case where over a period of time, my condenser is getting scaled, and now there is a back pressure of steam on the steam turbine. It will lead to generation of less electricity. So let's say that comes out to be 0.8 megawatt. If I'm burning only 1 ton of coal, I have to compromise on production of electricity, and it will be dropping down to 0.8 megawatt. So what do I do for this? Because let's say this is a power plant. I mean, let's just imagine a scenario that is serving Mumbai, and we can't be like in a situation that we say, okay, we will serve only 80% of the clients and 20% of the clients will suffer, will not get a power. That's not the option. So what does the power plant operator does? He just jacks up the coal. When he puts more coal, he gets more steam. When he gets more steam, even though there is a back pressure from the condenser because of the condenser scaling, he still is able to make 1 megawatt. So just that 0.2 tons per hour of coal is increased. Now, when we say that 0.2 tons per hour of coal is increased, that means that I have increased the CO2 emissions by 0.2 tons more. I'm just saying, just being equal, like whatever is the coal burnt, same amount of the CO2 emissions is there. So just, same way, if this condenser continues to scale more, even further, let's say it becomes 50% inefficient, the condenser, or 50% scale condition on the condenser. Guess what? The steam turbine will again have a more back pressure. It will produce less electricity, which is again unacceptable. So the plant operator will just end up increasing the coal to almost like 2 tons of coal. So this 2 tons will now relate to, emission of 2 tons of CO2, but there will be 1 megawatt consumption of, he has to make 1 megawatt no matter what, even if the condenser is scaled. And even if, you have to put more coal in, you still go ahead and do the needful, like whatever is needed to make 1 megawatt of electricity. Now, this just being the case, it sounds like really, the chemical engineer, it might sound like really stupid that why do you want to burn more coal? And instead of that, why don't you just, clean this condenser and be done with the, waste heat efficiency, make the condenser efficient, and always be running at a very low amount of CO2 emission, like just enough, basically, let's say 100% efficiency, so that there is a minimum amount of CO2 emission, and especially for the power plants in the suburb of Delhi. So let's say Haryana and all those areas. So when we went with this thought process to the NTPC, they were like, yeah, I mean, on paper, it sounds really good. But, we really don't know, like, how, how much is the scaling in the condenser and how to decide when to do the cleaning of these condenser, and what about when I'm doing the cleaning, from where I'm going to get the power when I'm doing the condenser cleaning. So these were the actually problem statement where we are taking the help of AI and reducing the CO2 emission. It is still in the decision making phase. It is not yet concluded. Uh, it takes time in to get this implemented, but it's pretty soon will be implemented. So you know so I'll just walk you through whatever I explained over here, the where we really took the help of AI and what were the benefits of that. So I'll just walk you through that. So efficient, if we are able to predict. So with the help of AI, so what did we did when we took the help of AI? What did we really did was we were able to really understand, first of all, at what efficiency is the steam turbine running with respect to condenser scaling. So there will be something like we call, that there is a term called fouling factor. So mostly RF. So what is the scaling in the condenser and what is the impact of that on the steam turbine, like efficiency wise, like what is the impact of that? So we were able to, first of all, generate a data that as the condenser is scaling, the efficiency of the steam turbine to make electricity, actually it is other way around. Let me just do this. So as the scaling is increasing on the steam turbine, sorry, on the condenser, the efficiency keeps on dropping. So we were like, first of all, able to gather the data that, really gave us this trend that as the fouling factor is as the fouling or the scaling in the condenser is increasing, the efficiency of the turbine to make electricity is dropping. Then after this data, what we did was we plotted another plot. As the condenser is getting scaled, the amount of coal consumption. So we found that as the condenser is getting scaled, the coal consumption is increasing. Why? Because we are making the steam turbine more and more inefficient. So it was demanding for more and more coal. Now, that being said, this is a pure correlation that as the condenser is getting scaled, there will be an increase of CO2 emissions. And there is one more trend that we observed was that as the condenser is getting scaled, there is more and more of money to be pumped in to coal, basically the fuel, to make that 1 megawatt of electricity. So if you look at it as a business case, I mean, there is no point in putting more coal in to make that same 1 megawatt of electricity when you can do it at a much lower scaling. If you have a lower scaling or RF, the scaling, then you just need to spend less money to make that same amount of electricity. Now you might ask me a question that why were they not doing it? I mean, since there is so many challenges with respect to the pollution or air quality in Delhi, why they were not doing it? Well, we we are getting this platform that all of you guys are chemical engineer, and for me it hardly took half an hour to explain you what is the scaling and what is the impact of the scaling, the condenser scaling on the coal consumption to make 1 megawatt of electricity. With the help of these graphs, I was able to explain you very easily. But the power plant, or the management that is making the decisions, are not really chemical engineers. So they need more data to do that. So what I understand was that on a very high level, they didn't had this data to begin with. They know that condenser are getting scaled and things are getting back pressure, and it is reduces the efficiency of making electricity, and it reduces the and it increases the cost for making that electricity. They knew that, but they didn't have all these trend to make a hypothesis that is this the really the case that is happening. So with the help of data collection, we were able to make this trends and make them understand that what is the where they are losing money. And these are big money. I mean, we are talking, if I have to just give you a number, we are talking, if the turbine, I mean, we'll see in the next slide, we are talking lakhs of rupees per hour. So I'm talking about, like, just to give you a number, like 10 lakhs per hour of more coal that we have to burn if we are not monitoring the scaling in the condenser and just running the power plant for the sake of making electricity because we are asked to do that. So that is the magnitude that we are talking. And if we further run the unit even more scaled, this 10 lakhs become 20 lakhs within a fraction of days if we are not monitoring it. So that is the magnitude we are talking. So it became more of a money making as well as CO2 emission. So it kind of tied together with the vision of AB engineers that we want to reduce CO2 emission. It didn't tie up with the recycle part, but it definitely went in the direction of reducing the CO2 emission. So that was the the overall reasoning for getting into the AI part and getting into the condenser scaling part. So it not only reduced the fuel cost for making 1 megawatt of electricity, it also reduced the CO2 emissions. And now with this type of model, the the owner. So let's say in, in NTPC, they have now they have something like this, that let's say in the state of Maharashtra, there are, I'm just saying to make it really simple. Let's say there are two, or not, let's not stick to Maharashtra. Let's narrow it down to Mumbai. Let's say there are two power plants that mainly serve Mumbai. Okay. And let's say one power plant. So let's make this one, and let's make this power plant number two. And there is a scaling. Okay. And one power plant has the RF value, the scaling. Let's say it is 100% means completely scaled, and 0% means completely clean. Okay, that being the basis. So let's say there is a power plant 2 which is running with 60% scaling, 60% scale condenser, and there is another power plant which is running with 10% scaling. Okay. Now, currently, this power plant has, both the power plant are of 100 megawatt capacity. I mean, they can easily run with 100 megawatt. Okay. Now, currently, they are running both the power plant at 50 megawatt. So power plant 1 is running at 50 megawatt, power plant 2 is running at 50 megawatt. The total requirement for Mumbai, let's say it is 100 megawatt. Now, tell me which power plant they should run and at what capacity they should run, so as to make 100 megawatt, have less coal consumption, means less money for making 100 megawatt, and at the same time reduce CO2 emissions. Tell me which. First of all, like you have option, like option 1, I'll give you run power plant 1 and power plant 2 as they are running, like 50 megawatt and 50 megawatt. That is, option 1, which they are already doing it. Option 2 is run power plant 2 at 100 megawatt. Option 3, run power plant 1 at 100 megawatt. What do you think, if you are the top level manager to make these decisions, which option would you go for? Can you give me an answer? Yeah, go ahead, Renu. Ma'am, can you unmute her if possible?
Yeah, Nitin, I hope if you're saying that power plant 1 is having a 10% scaling, so better we can run that, but you're limiting the capacity also one way, 50 megawatt. So I have a limitation on the
Actually, the
generation of.
power plant, both the power plant have 100 megawatt capacity.
Yeah, but currently you are running at a 50 megawatt.
Correct. Correct.
Yeah,
Correct.
so I think that is the design case would be 100 megawatt, but you are currently operating at a 50% with a
Correct.
10% scaling, because
Correct.
you don't want to scale more falling in the condenser side. That's why you are limiting up to 50 megawatt. But other you are saying it's a 60% already scaling is there. However, the
Correct.
capacity
On
remains
power
same
plant 2.
50 megawatt. So
Right.
better if we can run the first plant on the 70 or 80 up to limiting
Mhm.
the falling to 20% or 30%. Still, we are in
Right.
a better position rather than running
Correct.
the second power plant.
Correct. So you are, I mean, you nailed it pretty good. Uh, I think you really thought as a manager that you're operating these units and, came up with the solution. So you had something else to say?
No, I think the better efficient way is maximum
Correct.
utilization of a power plant one. Yeah.
Exactly. So initially, what I could understand from NTPC was that they didn't had something like this as a dashboard with respect to scaling and efficiency of the turbine, the steam turbine, to say that, oh, this is inefficient operation or this is efficient operation. They didn't had something like that to even make a judgment. Only when there would be a lot of back pressure from the steam turbine is only when they would come to a conclusion, oh, we can't run this power plant. We have to do a stop. And that would many time lead to we call it as a last minute stoppage, like unexpected stoppage. Let's put it that way, that there will be a unexpected stoppage and there will be there will be a lot of chaos because of that situation. So just to give you a context more of uh, just to elaborate more on this condition is that let's say you have two cars at your place. One car is a SUV which has a less mileage, and you have another as let's say Maruti Swift. You have that which has a very good mileage, and let's say you have to travel in a efficient way, more in context to low fuel consumption. Since Maruti has a Swift has a better mileage, you will go for something like since you are having a very long drive, you want to do a less CO2 emission, you will go for a Maruti Swift rather than a SUV. So this is, but since you had a tracking record of, okay, my Maruti Swift has a better mileage, you know that number, and you know the number, the mileage of SUV, you were able to take those decisions, which I understand that, these top level managers didn't had that access or that clarity of, how these different, what is the mileage of the plant? Let's just put it that way. What is the mileage of the power plant as it is running right now? So as to take a decision that, for example, in this case, just 1 minute now, just one. Sorry about that. Okay. So what I could understand from, from the power plant managers that they didn't had a way to really understand the mileage. So now with these tools, they are in a position where they can decide that, okay, I will completely shut down power plant one and I will sorry, I will shut down power plant 2, which is, 60% scaled, clean it, clean the condenser. In the meantime, I will run the power plant 1 at 100 megawatt. And, I'm still meeting the needs of Mumbai, whatever the power consumption or whatever is the power required by, for Mumbai, I am still able to meet it because I have my power plant 1 and power plant 2, both have a 100 megawatt capacity. It's just for some reason I was running this power plant 1 at 150 megawatt and power plant 2 at 50 megawatt. So now I can take a decision like, okay, my power plant 1 is acting more as a Maruti Swift and my power plant 2 is acting as a SUV. So let me park the car, SUV at my home, get it clean, the condenser, and in the meantime, by the time this cleaning is going on, I will take power plant 1 into full load capacity, 100 megawatt, and meet the needs that this plant is meant to required to meet. So that is how those decision making became easier. And I'll just show you in the next slide, like what was the benefit, just to give you a context here. So prediction, this was the dashboard that we were able to create as far as, prediction of the scaling in the condenser. So this prediction part, I will come to it later, but this is more in context to like what is the resistance or RF, the let's call whatever the percentage of scaling uh, in different months, like how that was going on. So we were actually able to monitor it. So get the actual scaling, whatever is going on. At the same time, like now I'm jumping into something else, probably a little bit of a difficult term to hear, but I'll still add it. There is something called machine learning in the world of, let's say, AI. So what does this machine learning does? Uh, to put it into a very, very simple context, what is machine learning and how it is applicable over here as a chemical engineer? Again, I am also a layman in terms of AI and machine learning, but the way I taught myself is something I'll use to, give you an example. There is a prediction of stocks, like what will be the price of stocks in the market. So if you go into the share market and you are in the game of making decisions, how to which stock is good, should I invest in it today or should I withdraw the money from it today? How do I know? So there is people in the software or IT have figured out something which is called share price prediction. What will be the share price in next day? And is this share price going to increase or decrease? All those kind of prediction. How are these predictions really done? They are done based on the past data. So gathering, the data of actual price throughout the year in a way, and then putting it into a model which is similar to machine learning model. And that machine learning model will be like a robot basically who will send out the values that, okay, at this time of the year, this particular share price last year was like this. So this year it will be like this, like whatever. Or if I have to, you know, give you another best example of this prediction thing is, nowadays when we are doing a ticket booking in, like let's say if you're using Ixigo train or Trainman or whatever app you're using, you will see a prediction. Like there is like today the ticket is in wait list, let's say 5 number waiting. There is a fair chance of this getting confirmed, and it will give a chances like 90% or 99% chance that it will get confirmed. So how did it do that? How did it calculate it? How can it predict the future? So what it did was, based on past year data. So let's say I'm traveling in January, on let's say 26 Jan, I'm traveling and I booked my ticket and I got a wait list of 5. And this is 2026, this year. Last year, on the same day, 2025, when there was a wait list of 5 for this particular train, it was confirmed. So it has that data. So this all data has gone into a machine learning model. And based on that, it does a prediction that there is 99% chance that there will be a confirm of this waitlist 5. So that machine learning plays an important role. In a nutshell, you're training the model, and then at the same time, you're taking the output from the model for throughout the year. So similar thing, we did it on the scaling in the condenser, that we took the data from Jan to all the way up to December. What is the scaling? If you look at the blue one, this is the kind of actual scaling, and the yellow ones are the predicted one based on the machine learning model. So becoming kind of very, it's a good prediction to plan the shutdown of the power plant for cleaning the condenser, or any other part of, shutdown activity, keeping in context to condenser. So I do want to, like, I didn't mention this earlier, like there are many other things that drive the efficiency of the turbine. But this is one of the major thing. Condenser scaling is a major thing that contributes to the inefficiency of the turbine. So that is the, basis of selecting condenser scaling. So this prediction again helps the very high level power plant manager who are responsible for, let's say, Mumbai area or entire Maharashtra, that let's say we have uh, 50 power plant in Maharashtra. And if we want to decide that, which of these power plants we should be running and which of the power plants we should put it in standby or shutdown for cleaning or any other maintenance activity, this prediction helps a lot. And this prediction is really done by the ML, the machine learning. So I will get into more the sequence, how this was done, but this is like one of the benefit of using, AI into reducing the CO2 emission, and at the same time making power at a very at a best economical cost. So yeah, so let me go on the next one. So this one was again like a prediction if we are running, and this supports kind of this one, that if we are running the power plant at a inefficient or more inefficient conversion of fuel to electricity, then this is the excess coal that we are talking about. And this is like in crores per month that we are talking about. So, and then even more than that, because of this excess coal consumption, you're also dealing with excess CO2 emissions. So these are the key pointers that we were able to do with the help of AI into the prediction of the condenser scaling, and giving a leverage to the power plant manager how they can decide the scaling in the condenser. And at the same time, they have a plan of action. Like, okay, I will, since the condenser has, and there is also like something we created was an alarm that if a particular plant out of the 50 plants, let's say in Maharashtra, one of, or let's say, 10 power plants have reached the threshold of 60% scaling, there will be an alarm or an email shooted out to the manager that, hey, this is, coming to 60% scaling. We have to make some decisions, whatever, within a month or within next 2 months, because this will be emitting CO2 like anything, and there will be a cost implication because of burning of the excess of coal. So this is something that became very fascinating to all the higher ups, more on power plant managers who have to decide like which power plant will be running at what capacity. So for example, the inefficient power plant, the 60% scale power plant, they had the luxury now to decide that, okay, if I'm not able to shut down this unit, I will run it at a bare minimum capacity, so that, let's say if I have a 500 megawatt total requirement, I will run all the power plant with more than 60% scaling at just 5 megawatt, and hence put in less amount of coal, less amount of money for the coal. Anything that is greater than 10% scaling, I will run it at a maximum capacity. This way, they are able to, make 500 megawatt with the best possible plan for less coal consumption, less, making more profit, and at the same time doing less CO2 emission. So this was, kind of their kind of the luxury that they were getting uh, once they are going to get into this thing. So any questions so far? Anything? I think I'll show you the next one.
Nitin,
Yeah.
so I have question. Like you mentioned, based on the prediction, we can limit the use of a coal. Rather than
Right.
that, can we automate the system? Like if we have a more pressure drop in the condenser side, we can limit the coal input. So that way
Yes.
also we can control why you
Yes.
need
Yes.
ML or these data, or we can take a direct switch over the next condenser. So similar sort of automated arrangement rather than like a sys or
Right.
more
Right.
safety loop. Why we are
Can you
looking for ML?
can you elaborate? Yeah, can you elaborate more? I mean, this is a good one.
Yeah, like in a exchanger, you are saying it's a falling factor is increasing. It means our pressure drop is getting increased. Correct.
Perfect. Perfect.
So
Yes.
if your pressure drop is increasing, you can limit the coal input, or instead of getting the same lineup of this condition, we can switch over to the next condition which is having a less scaling. So switch
Hmm.
over of a
Hmm.
condensers. So it's automated instrumented loop.
Right. 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 Okay. Okay. I got your question. So I mean, just to add here,
Mhm.
many. I mean, see what you're saying is perfect. I mean, there is nothing. I mean, it's a good one. What I understand is that these power plants are really old, so they have only one condenser. They don't have like a
Backup.
luxury of two, but they like they can go for that in future. Put another one and go for future. Uh, that is one thing. Then second thing, like you said that how can we automate the coal controls in a way?
Yes.
Yes, but what I understood is that the way the infrastructure is in the power plant, they are just given every day or whatever monthly or a weekly target that you have to make this much power. Like if for example you are chosen out of 50 power plants in Maharashtra, you're chosen that you have to your power plant is the one that has to make 100 megawatt. Then it's like a bullseye. Even down to production manager, they will not look at what is the coal consumption. They will be like, okay, I have to make that no matter what. So they will not even, it's a wrong statement, but it has been observed that they won't even care what is the coal consumption. I just have to make 100 megawatt. Why? Because if I make less than that, then there will be a penalty on me. So there is something called balancing of the grid. Like they each power plant are committed to make this much amount of power to keep the grid balanced. So for us as a chemical engineer, the nomenclature means that I have to keep the energy balance. You know how we have the energy
Mm.
coming in is equal to energy coming out. So same way in the power plant, they have a grid where the amount of electricity consumed has to be made up by
Production.
production. There can't be like a cycle, like one power plant because of, let's say, because the condenser is scaled, automatically the coal consumption, let's say, will go lower so as to keep the CO2 emissions low or the cost of fuel low. Then that particular power plant will face the challenge of making less power, and that is unacceptable. They will face the penalty. So, like and let's say on the other side, if the condenser is really clean and they say that with this much amount of coal I can make even more power, let me make more power. They can't, because again there is a penalty if you overproduce the power. Why there is a penalty? Because now the grid is getting energy in is more than energy out, because all the producers are making the amount of power that they are asked for. Only this particular power plant is making more, but just because they have a more efficient condenser or a more efficient fuel to electricity conversion. So it's not by their choice. It's kind of penalty on the lower side as well as on the higher side. So that is the baseline for this. So that control part is again, that freedom is taken away from them. So that is why at least what I saw in the market is that they really don't care what is the coal consumption. They just care that I don't need to suffer a penalty. So they are just after making that whatever is the target megawatt and be done with it. Don't look like, whether it is inefficient, efficient, that is like higher ups who is deciding, giving me the target. If he's the one who is deciding 100 megawatt, he has something thought. Normally, what has been thought is they do get the coal bills, the fuel consumption bills, the upper manager who's deciding, like, these 50 power plants at what capacity they will be running, they just look at the fuel bills and decide. But by the time they get the fuel bills, it kind of gets pretty late in the game, because last month fuel bill is, you already paid that cost for inefficiency, and now this month you are kind of taking an action based on the old fuel bills. So there was not a data collection per se. So that is the context for that. Yeah. Does that make sense?
Yeah, yeah. And the second thought coming in my mind, that can we put any treatment package because we are only talking of the corrosion. So rather than putting it directly to the condenser, before that we can put a water treatment package so we can reduce the corrosion inside the condenser. That is the
Correct.
other way.
Correct.
Yeah. Again,
Correct.
it's a cost. Again, it's a additional cost. But yeah, that way we can improve the
No, I
efficiency,
mean,
coal consumption.
yeah. See, eventually, I mean, you nailed a very good point that, in fact, there is movement even on that side, that the inhibitor or I
Yeah,
think
pH
it
treatment, chemical
pH
treatment
treatment,
package.
and the anti-scalant.
Correct.
So all these are also getting into this AI zone thing,
Mm-hmm.
where they are monitoring the water composition, and based on that, automatically tweaking themselves to mitigate the scaling.
Mm-hmm.
And they are definitely like a very important one, like, and it is being done. To be honest, it is being done.
Okay.
uh, I don't remember right now the exact word, like, it can even measure down to the active ingredient of the anti-scalant.
Mm-hmm.
If the scaling increases, this active ingredient will get consumed, and based on that, the dosing pump of the anti-scalant will, go up and down.
Work. Mm-hmm.
So it is actually done to that level. Like, I think Nalco is doing that,
Yes.
and they have like actually like a very big control room in probably Pune or somewhere, where not just India, but even some parts of the globe in various countries, they will be monitoring this. And based on that, they will be monitoring, like, what is the health of the scaling part. But they will restrict themselves only up to the scaling part. They will not monitor the in terms of the total electricity efficiency, like conversion of fuel to the electricity. They will not monitor that entire part. So, but it is a important one. It is an important one, and because what happens is, if throughout the year, if I'm doing this chemical treatment and tweaking this chemical treatment using, let's say, AI, or machine learning, or we just monitor the active ingredient, if we are able to do that, and I'm getting the runtime before we hit the threshold of 60% scaling, and let's say we get that runtime extended to 2 years, that means I can run my power plant for 2 years without taking it out of service for cleaning, for any of the maintenance activity per se, and keep that power plant efficient for higher efficiency from fuel to electricity conversion for 2 years. Versus, if I don't have a good treatment system, my life of the condenser before I have to take it out for cleaning might be only 6 months. So it plays a big role. That treatment plays a big role. Uh, what this particular thing that we did is it helps you to just monitor and take decisions. That's all. It is nothing like it is not physically going and doing the controlling of any of the power plant. It is just monitoring it, and like a stock market or like a prediction of the wait list for the train ticket. What will be the possible? What is the best combination I can run the power plants in Maharashtra so that I get a good fuel efficiency from all the power plants that I have. At the same time, if some power plant needs to be taken care in terms of cleaning, have that margin to or planning to do that. Like, okay, 1 month down the line or within 2 months down the line, I have to do that cleaning. That planning became easier, which earlier was not there because there was no prediction and there was no actual data on the table. It was all actual data was there, but it was for like past 2 months by the time they get the fuel bill and all that stuff. So it would be you already has spent crores of rupees before. It's like you already damaged and now you're further saving yourself from doing the more damage. So that was the concept earlier. The water treatment was already there, and it is getting more and more advanced now with this AI, but that is already there. Yeah. So if you have any question, shoot. Otherwise, what I will do is I will show you down to the nut bolt level how this is actually done. I mean, and where the equations have been really applied related to chemical engineering, how they are really applied more in a layman language than going into all that ML thing and everything. Because to be honest with you, like those ML thing were all we did study, but we took lot of help from Chat GPT and all that stuff to really put that together. But I'll tell you where we stand apart uh, when we were doing this. So, but tell me if you have any questions so far. Otherwise, I'll jump into that topic. I don't think you have questions, so I'll just jump into the like the PFD, what we did. So for if you remember the the way from heat transfer, if you remember the equations, let's say this is my condenser, this is the steam flow. So I'll just put MST as my steam flow. This is my cooling water in, and this is my cooling water out. This is let's say mass flow of cooling water, and let's say these are the temperature, and there is this temperature saturate, and then there is PSAT. PSAT is the operating pressure, and at this saturation pressure we have the saturation temperature, and this is the mass flow of the steam coming from the steam turbine. So how did we calculated RF, the fouling factor? So what we did was we did a mass balance and energy balance. Q is equal to MCP delta T for the cooling water. And we did the mass balance or energy balance, that is Q is equal to M into lambda for the steam. Now we once we got the Q, we did that as Q is equal to UA into LMTD. And we basically calculated the U as a clean and U as the service and U as the dirty condition. Okay. So there will be, I mean, there might be some nomenclature thing that I'm just trying to generalize here, just to make it for the ease of understanding. But this was our main model. And then what we did was back pressure, that is PSAT clean, PSAT service, and PSAT dirty. So we used these two parameters for understanding what is the, health of the condenser. And initially, our goal was to understand actual data of PSAT and U. Okay. And we started when it was completely clean condition. Over a period of months, we understood that, what is the good service PSAT and U for it. And then we decided one as the very dirty one, like I would say scaling more than 60% is what we called as a dirty. The service one, optimistic, we decided that more as the 30% scale. And this is clean is 0% scaling. So that's how we categorized. But we took all that data. We took all that data into cloud. Okay. So now, do you have any questions, or else I'll just jump into how we did that just to make more sense. I'm guessing it's a no question. So I'll just jump into like what did we did to, or more in this is where I really wanted to focus on in today's presentation, like how this is really done. I mean, this all looks good on the paper as far as the formulas. I mean, but physically, how is it done? So what we did is we put a electromagnetic flow meter to measure the mass flow of the cooling water. Okay. Then we put a PT100 temperature sensor to monitor the temperature of the cooling water. And then we put one more temperature sensor, PT100 type, in the outlet of the condenser on the cooling water side. So that helped us to give this equation. Like this is that, MCP delta P on MCP delta T on the cooling water side. So this is what these are the instruments really involved for measuring the temperature and the flow across the condenser. So I happen to have those temperature sensors with me. I'll just show you that. Just 1 minute. So I don't know if, yeah, I think you can see it. So this is the, let me do, yeah, okay. So this is the PT100 temperature sensor. And this temperature sensor is by IFM. So we use this two temperature sensors to mainly monitor the temperature of the cooling water going in and temperature of cooling water going out. Now you might ask, okay, we are sending this data, this temperature sensor data into the cloud for retaining the historical data of what was the temperature, let's say last year in January 2026, what was the temperature of the cooling water in and out? What was the scaling? What is the back pressure? Let's say we want to know that. How to do that? Uh, Typically, I'm not going to go into that depth, but I'll just say that cloud nowadays is a more easy way. And if you think about it, more in context to the railway reservation where the prediction is done. I'm going back to that example, where last year wait list of 5 can be predicted that will it be confirmed or not. How was it done? It was basically by the historical data stored on the cloud. So that gives you a context that why storing the data on the cloud became important. So now that being said, this is that final, temperature sensor that takes the data. What it does is it goes into a PLC card of this type. It goes into the data goes over here inside inside the card, the PLC card. So let's say this one is mainly to take the data, a physical sensor takes the data, sends it to the PLC. Now this PLC is connected by another piece of hardware, and this hardware or PLC, I'll just use the word PLC to make it simple. This PLC is then connected to the internet. And let's say it is connected, just to make it simple, it is connected to, let's say, Google Cloud or AWS, the Amazon Azure. And this data is being stored over there on the cloud. Now, This is the, now one thing I want to add here is that even the flow meter, the magnetic, the electromagnetic flow meter that we have is also connected to this PLC only. And even that data goes to the cloud. So like that, all the data is going to the cloud. So just keep in mind that, this is just bare naked data going to the cloud. There is not yet any calculation done. Or if you ask me, this particular thing, why I wanted to introduce this to you was that this is typically the job of instrumentation engineer who is doing the programming of the PLC and all that stuff. We as a chemical engineer are never exposed to that. But if we know what these guys do, how I can use these piece of device to store the data on the cloud, it makes life easy to apply this thing in variety of other applications, like what you have been seeing in last 2 days, and eventually even later on today, tomorrow, you will see more like how this can be applied. But what I felt is that these are the important things, that the temperature sensor getting connected to the PLC to the cloud are very important. Once they are on the cloud again is done more by some IT or computer engineers to get that data stored and everything into the way it has to be. After that, there is something called once these data are being stored in the cloud, there has to be some calculations done on this data to give me PSAT clean, PSAT service, PSAT dirty, you clean, you service, you dirty. Those calculations are defined by us as a chemical engineer. Like, you have to tell the IT guy that okay, you have collected the data, so let me clean this up a little bit. So let's say we temperature transmitter, TIT, sends the signal to a PLC. PLC sends the data to the internet, and then the internet stores the data on the cloud. If you look at it, this temperature sensor is defined by the chemical engineer. This PLC is programming and everything is done by the instrumentation engineer. This part, traveling to internet, traveling to cloud, is done by the IT engineer. Now, when this stuff is stored in the cloud, the equations for PSAT and U is done by chemical engineer. Secondly, this entire game of which data to be taken to the cloud, what should be the equation put into the cloud, the entire concept is by chemical. So that is the way to, look at things, or that is the way to really, look at how this is applicable and where do I stand in this AI world? Where does, a chemical engineer stand in this world of this whole, the AI thing? So this, now I'll just elaborate, go a little more deep on the cloud part. Again, when I'm saying cloud, don't think that, we have to do cloud programming or anything like that. If you do, best. It's the best thing to do. Get your hands on, get your hands dirty, and it's the best thing to do. But if you don't, you definitely should know your concepts on the chemical engineering side, because you have to tell the cloud engineer or the IT engineer how to apply these equations. Okay. Now, there is something called error handling. Or it is also called data cleaning, where a chemical engineer plays a very, very important role. It can't be done by, when I keep saying it can't be done by, computer engineer or IT or instrument, anything can be done by anybody. But it is, when I say it can be done by chemical engineer, means it is very easy for a chemical engineer to understand, and it will take maybe a 10-minute thing to understand by a chemical engineer, whereas the other faculty engineers might take at least, a week or 2 weeks studying different articles and different papers and then come to a conclusion. So that is what I mean to say, that it is where chemical engineering or chemical, faculty plays a very important role in understanding and interpreting. So what is data cleaning? Now, since this is a temperature transmitter or a temperature sensor, there is a chance that so let me first put into context what I'm talking about. What is data cleaning really? So what is data cleaning means is that any data after doing the calculation, like Q is equal to MCB delta T. Let's say we did this calculation for cooling water to calculate the Q. There is a chance that some of the sensor are giving a garbage value and the Q calculated will be garbage. So how to filter that out is defined by chemical engineers. How is it defined by chemical engineers? So in anything that you're calculating, you are doing a multiplication, you're doing a subtraction in the delta T. And sometimes, let's say you're doing a division. Data cleaning means any equation calculation by the computer leads to a value of 0 or infinity has to be cleaned up. So those garbage values are defined by the are basically defined by the so those garbage values are really defined by the chemical engineers. How are they defined? So let's say we have temperature of cooling water coming in, temperature of cooling water going out. For some reason, let's say the temperature of cooling water coming in is 35 degrees C and 35 degrees C of cooling water going out. For whatever reasons, we don't know, because of the temperature malfunction or the power plant is gone in standby, whatever, we don't care what is the reason. If this is the scenario, this data will lead to a value of 0 in the calculation. So this has to be cleaned out. This has to be basically discarded data. This can't be used for our prediction or any other further modeling or even storage of data. We don't even want to store that type of garbage data. Okay, so that is that. So what does a chemical engineer defines? He defines to the programmer that cooling water out minus cooling water in, sorry, if cooling water out is equal to cooling water in, that's equal to a garbage value. Don't even calculate the Q, because we know that it will be 0 and it will be garbage. So directly delete that data. Don't even consider that data. So this thing is defined by a chemical engineer. This is where there is a role play of the chemical engineer. Now, another example. Calculation of U. U is equal to Q divided by LMTD. Now, if for some reasons, again, LMTD is equal to 0, this will lead to an infinite value. So the chemical engineer defines that if for any reason, first of all, the LMTD should not be 0. If for any reason this happens, this will be a garbage value. Same way, if the mass flow in this Q is equal to MCP delta D, if the mass flow is 0, this will be a garbage value. Don't even consider, spending time on, considering this. So like that, these equations are for data cleaning are defined by chemical engineers. It cannot be, it is very easy for a chemical engineer to understand this and go from there. So I just wanted to now, use my last bit of time on very high level. What do we do with the cloud data? Yes, one job of the cloud data is to store and give you the actual value. So let's say if you open up there will be a dashboard screen telling you, okay, this is the thermal efficiency, this is the fuel consumption, and this is the scaling. Okay. The other job of this cloud data is to give this data to a machine learning model. What does this machine learning model does? It gives an equation for predicting the future values. It is not so, and this is also on the cloud only. And there is another dashboard which does the job of the prediction. So just to give you an example of these dashboard that I'm talking about, what is that really that dashboard? So this is really that dashboard. The blue one is the actual data on the cloud, The yellow one is the predicted data by ML model on the cloud. So this is, I'm just summing up the whole thing that, I talked about was the role of chemical engineer. He decides what will be the instrumentation needed. If he wants to save on the fuel, save on the CO2 emissions, he decides the equation inside the cloud for data handling or data cleaning. He also has a role in machine learning model, the ML model, and do the prediction. One part I missed is he also defines the threshold value that if the scaling is more than 60%, then send an email or trigger an SMS to the concerned manager so that he can take actions accordingly. So, but that threshold is designed or defined by the chemical engineer. So this is, what we are doing at, kind of at AB Engineers as a part of our vision for reducing CO2 emissions. Yeah, I mean, I just want to roll it over to you guys for any questions. If you have any questions, I can answer. I mean, I took little bit speed on the ML part, but I think it's I mean, it's something you can easily crack it. It's not a very challenging thing. So I think important part where I felt the gap was knowing how this transportation of the data is from, first of all, what is the purpose of doing the AI part? Basically, profit, reducing the CO2 emission. Okay, we got that problem statement. How did we work on it? We nailed it down to the instruments that we want so as to predict, sorry, get the actual data for back pressure, get the data on the U fouling or RF, and then put it into the cloud and then put it into a ML model and then get the predictive one. So that was my whole idea on, yes, finally give you a few concepts that will go beyond your head on the ML part or cloud part. But I think you should know. And the best way I tried was giving you an example of this Ixigo train if you have used it. Or let's say you're trying to on Google Flights, when you try to check the cost of the Google Flights, it will give you sometimes even the price of, or even on, yeah, I think Ixigo is the best example. Like if you're at a waitlist 5 and you want to know, should I travel on that date or not? Or should I, rather than going in the train, should I go for a flight? It gives you that leverage that it gives you a prediction. And based on that, you can decide like, should I go or not? So I would just say that treat the ML model, the cloud data, not as a heavy concepts. Just think that it is like the Ixigo or prediction app that it does the job of that. And then you can take your judgment that which part should I go? Like, should I run the power plant 1, power plant 2? And like, the first example that I gave you, like, should I run both at 50 megawatt or should I run it at first power plant at only 100 megawatt. So that was, I think that was the best way. to explain and summarize. Yeah. Over to you guys for questions.
Participants, please feel free to ask your doubts or questions. You may post it in the chat or Q&A section.
Thakur Sahab, Rajesh here.
Yes.
I'm from oil and gas EPC background. Just as
Good
this
afternoon,
problem
sir.
is related to human lives in Delhi. Just
Right.
one point, based on my experience, what I want to suggest that there is a scaling, and scale is coming out of steam. So generally it will be calcium and magnesium sulfates, chlorides.
Right.
These scales we generally found in boilers.
Right.
So I think it is a good idea to actually analyze the composition of these scales, because this NALCO, we also use their chemicals in many oil and gas projects. They are many times costlier, NALCO, Baker uses.
Right.
So if you see only sulfates, chlorides of calcium, magnesium, then you get these treatment chemicals. Okay, local makes also cheaply. First point. Second thing, what we do in operation, what we see here, that these are big scale, in terms of quantities, fluorides are very high.
Correct.
So online cleaning, that will not be possible. Generally, what we do in case of adsorption cycles or even filtrations, that nutshell filter, regeneration or say backwashing.
Right.
So that sort of, can be checked feasibility of that the turbine
Right.
which is connected to condenser, which is 100% fouled, to bring it to turn down
Right.
capacity, purge or that steam to the atmosphere through the silencer. Okay, means what I'm saying is isolate that condenser.
Correct.
And there, you inject online cleaning along with the water, because that scales, with the anti-scalant chemicals that will be soluble in the water. Even, these boilers will be high pressure systems. So purging nitrogen, okay, to make a turbulence there for improving solubility, that can be checked.
Okay. Yeah.
So rather
Very good
than,
idea.
annual cleaning, it will
Yeah.
be monthly or twice monthly cleaning, so
Correct.
that, your scaling does not exceed 20%. So
True.
your this breakdown or turnaround time, it becomes, 2 years.
Turn down. Yeah.
So that it,
Yeah.
so that can be checked, just as a
Yeah.
concept
Yeah.
I'm giving, because, we are also reading in newspapers
Right.
about heavy pollution in Delhi. Thanks very
Correct.
much. Your lecture is valuable and detailed
Right.
one.
Thank you. No, these are very good inputs. Actually, these are very good inputs. Thank you for that. Yeah.
Yes, participants, any other question? So I think, Professor Sangeeta, if the participants do not have any question, we can wind up the session. Professor Sangeeta, you there?
Yes, ma'am. Okay. So very valuable and informative session, sir. Thank you so much. Now, on behalf of the organizing team, faculty members, and all participants, we extend our sincere thanks to Mr. Nitin Thakur, CEO of AB Engineers, for sharing his industry experience, practical insights, and forward-looking vision while staying deeply rooted in engineering fundamentals. Thank you, sir, for reminding us that future of industry belongs to those who respect the basics, question assumption, and use the technology with purpose. Thank you so much, sir.
Thank you. Thank you for the opportunity. Thank you, ma'am.
Thank you, Nitin.
Thank you. Bye.
Participants, do join for the next session on time. Next session we will be starting at 2:30.
Yeah, and sorry for the delay. Yeah.
Oh, that's fine. That's absolutely fine. No problem.
Thank you. Bye-bye.